So in the last video, we talked about how if you were traveling in a circle around a point, you had a centripetal acceleration pointing towards the center of the circle, and that was sort of keeping you, that acceleration towards the center was keeping that circular motion. Well, it shouldn't come as a surprise to you after last chapter that if there's an acceleration, there's also going to be a force. So remember, forces are mass times acceleration. So centripetal force is going to be mass times centripetal acceleration. Centripetal force is also going to point towards the center of the circle. So that's the thing that is keeping us in a circular path. Okay, that's kind of an important definition there. Centripetal force is the force that's keeping us in a circular path, right? It's what's constantly pulling us in a circular path, even though we may want to go off in a different direction. If you remember from last time, we had a different way of writing centripetal acceleration. We can plug that right into our equation here to get that centripetal force is equal to m, and we knew that AC, our centripetal acceleration, was equal to v squared over r. So we get mv squared over r. So centripetal force equals mass times v squared over r. The other way we could write that, there was another thing that centripetal force was equal to, and that was r omega. So we could say that centripetal force is also equal to mr omega squared. Oops, I forgot my squared there. So mr omega squared. And so that can also be an equation for centripetal force. So now we want to take a look at the role that friction can play on a curved path. On a curved path, maybe we'll picture a curved path like this, and we'll say it has a radius equal to 40 meters, so kind of a big path. And we're going to have a car that wants to go around this path at a speed of 20 meters per second. Now, when a car is going around a circle like this, we kind of have to think, well, what's keeping it on the road? What's keeping it in this curved path? Because whatever's keeping it on the curved path is our centripetal force. Well, what's keeping it on the curved path, what's constantly forcing it towards the center of the circle rather than sliding out, is friction. And static friction in this case, because we're not sliding the opposite direction, right? We're not sliding out from the circle, so it's kind of keeping it in place and holding it there. So we may want to know, well, what's that coefficient of static friction that's necessary to make this happen? Well, start with Newton's second law. Sum of our forces equals mass times acceleration. Well, all of our forces, we have our centripetal force that's pushing it towards the center, and we have our friction opposing that, so in opposite directions. And in that direction, and sort of constantly towards the outside of the circle, there's no acceleration ideally, so that side of our equation is 0. So we know that our centripetal force has to be equal to our static friction. So centripetal force is coefficient of static friction times normal force. Remember, our centripetal force is mv squared over r times coefficient of static friction. Normal force, since we're on a flat curve, is mg. M's disappear, and so we get our v squared 20 meters per second squared over our radius of 40 meters. Coefficient of static friction, 9.8 meters per second squared. And you guys can solve from there to get your coefficient of static friction. So that friction is our centripetal force in this case because it's keeping us on that curved path. On a banked curve, we have a slightly different story, and this is actually why, when you go on a highway or on racetracks, you see banked curves, is because that banked curve is actually going to help you turn at a high speed. And the reason that happens, right, if we look at our normal force pointing off this direction, right, perpendicular to that surface, that banked surface, notice that part of that normal force is pointing towards the center of that curve. So the normal force itself is actually helping out with that centripetal force. It's actually giving sort of an extra little boost towards the inside of the circle. And so that's why they bank curves, is to help you turn at higher speeds. So let's consider for a moment that this is a frictionless curve. So there's no friction on it whatsoever. We can still make the curve without sliding because of that normal force pointing towards the center. So without friction, we could say that our normal force times the sine of theta is equal to our centripetal force, which is mv squared over r. So that's that horizontal component here that's pointed towards the center of the circle. And then the other component of our normal force, the cosine component, would be equal to the object's weight, which is mg. And then let's do a little math here, and that's solve for normal force. So normal force is mg divided by cosine theta. And then we're going to take that and plug it into normal force here. And we'll bring our work up here. So that we'd get mg times sine theta over cosine theta equals mv squared over r. Well, our masses are going to cancel out. And sine theta over cosine theta is tangent. So tangent theta, if we move our g to the other side, would be v squared over gr. And so that's how you can figure out maybe what angle do I need to make a certain turn at a certain speed if I don't have any friction. So this is a nice, useful equation to have here.